Welcome, everyone. I'm enthused and honored to introduce our plenary speaker this afternoon, Lukasz Miroslav from Microsoft Azure in Switzerland. He will speak about Exaflops achieved, what's next in supercomputing to address humanity's challenges. Lukasz is an expert in high-performance computing and artificial intelligence, where he's worked at Microsoft for over 16 years. And he has broad experience. He completed a PhD at the Institute of Cell Biology and Warsaw University of Technology. And after that, he held 2 postdoc positions at the University of Zurich in computational chemistry. He holds a variety of grants, including from the Max Planck Society, the Herbert Quandt Foundation, Saxony Ministry, and the Polish-Swiss Research Program. Currently, he is a member of the Global Black Belt team at Microsoft Azure, which is driving the most advanced collaborations in HPC and AI with industry and research institutions. So, without further ado, welcome.
Hi, everyone. Thank you for the introduction. So, what I will try to present today is 2 use cases from our projects. We work a lot with different kinds of partners. But before I do that, I try to define the key human challenges. Then I will end with some biased opinions about what is coming next for HPC. There are about 7 billion people in the world, spread in different continents. According to the best practices, we shouldn't actually split them into developed world and the rest. We should actually split the population into different income levels. So imagine you are on the income level 1. Your kids are walking barefoot. They have to walk 1 hour to get water from the nearby mud hole. You can't really afford buying food. You have to grow it. So you eat porridge every day on a bonfire. So your kids have also to collect wood. If somebody from your family gets sick, you can't really afford getting a medicine. This is extreme poor. The game of let's imagine you are on the level 2. You quadrupled your income. You have now $4 a day. What would you do with $3 extra? It's a lot of money. Well, you could buy a stove so that you don't have to collect wood. You could buy a chicken so you can have eggs. You could also buy a bicycle and get water maybe half of the time. At some point, maybe your kids can go to school. Okay, level 3, you made it, you quadrupled further your income. You have now $16 a day. It's a amazing savings potential. What you can do with that, you could actually get access to electricity grid. So it means you can get a fridge. It means you can actually provide different types of food every day. You can get tap water. You can also so it means no more fetching water from other distances. You can actually also buy a motorcycle. At some point, you can go to the local factory and earn much more. And you can send kids to the school. So when they finish the school, they will earn much more than you ever earned in your life. And then we have level 4, which is more than $32 a day. Everybody in this room is probably, if you are in this room, you are on level 4, which means you have more than 12 years of education. You can buy a car. You can actually, when you travel, you can use an airplane. So this is you are a rich consumer. And the game of life is actually moving from level 1 to the upper level. And before I move further, I would like to ask you 2 questions. The first question is, how would you place those figures representing 1 billion person to those different levels today? So please try to answer this question for yourself. And the second question, what is the average lifespan today? How many years a typical person lives today? So this is another very nice visualization of our current situation. This is a world chart of wealth and health. North and South represents healthy and sick, and east and west represent rich and poor. And as you see in 60s, so about 60 years ago, all the population were in the income level 1. So every bubble represents a country, and the size of the bubble represents the population. So let's have a look how we evolved in the last 60 years. So as you see, those countries are moving from income level 1 to income level 2, and even some of them move to income level 3. So right now, we are ending up in the situation that most of the population is actually on level 2 and level 3, which is great. In terms of life expectancy, today it's 71 years old. Typical person lives about, on average, 71 years, which is even after pandemic. And if you compare it to the generation before, that is really good progress, 10 years. And then if you compare further to 50s, it's really great improvement. So this is just that 2 metrics, but there are other metrics. So these are additional 6 questions that you could try to answer for yourself. What % of children are dying before the 5th birthday, approximately? Would it be 25%, 15%, 5%? The answer is less than 5% today. Why? Because most of the kids are getting access to vaccinations, and also the access to the public health system is even getting better and better. The last question is about poverty. Has it halved? Has it doubled in the last 20 years? Well, the answer is it has halved. So right now it's about 9%, even after pandemic. The next question is about what percentage of girls are enrolled in the primary school, 40, 60, or 90%? The answer is 90%. We made a huge progress again in the last 40 years. The next question is about being hungry. What is the percentage of people that suffer hunger? And it's 11%. What is the number of annual deaths from disasters? We are talking a lot about extreme weather, and it's actually 10 per million, which means we did a great job adapting to the extreme weather conditions. What is the reason for population to reach 11 billion in the next 80 years? Because of more children, more adults, or more old people? Well, the answer is because of adults. Why? Because if you are in the families in the level 2 and 3, they tend to have less kids because they can actually be dependent on the public system. So there are less and less kids, and in our part of the globe, some kids are not being born, and some kids are not allowed to be born, like with the Down syndrome. So it's really dropping. So those questions belong to actually so-called sustainable development misconception studies. These are just a few questions out of 18. And if you got the right questions, you can be really proud. If you got it wrong, don't worry, because most of people got it wrong. The average correct score is about to answer for 3 questions. And this is worse from the person who doesn't see the questions. He can just, he randomly answers. So it's an average monkey. And only 7% scored better than monkey. And what is really striking is that it's not only regular people got it wrong, but also United Nations experts got it wrong, European Commission experts got it wrong, journalists got it wrong, and even some researchers got it wrong. So this is the situation, and we are suffering from those systematic misconceptions. Why we are suffering? According to Professor Hans Rosling, is because of our different instincts that are incorporated in our mindset. And because of those instincts, we are really struggling to get a fact-based worldview. Our worldview is most of the time based on emotions, some of the research, of course, but many times on emotions and opinions. And out of the list of different instincts, I would like to just mention a few. The gap instincts is when we try to, let's say, when we are labeling people to belong to different groups. And we discussed it yesterday evening that we are building fences and we are not talking with the other group. If they have different opinions, we are not talking. There is no discussion between us and them. The second type of different instincts is negativity instincts, which is our tendency to notice the bad more than the good. This is very clearly monetized by the media, that they can get much better, much higher amount of views and clicks if they publish something negatively. And this is also a challenge because we have a single perspective instinct, which means we are performing our worldview based on a single source of single source, like on the media alone. Last but not least, there is a fear instinct. So we are, since 80s, as you remember, we are frightened by so many different effects. First it was overpopulation, then it was ozone hole, then it was global cooling, then it was resource exhaustion. Constantly we are being frightened by some scenarios. This is also a slide where I try to encourage everyone, including me, to double check the facts, to check always the source of information, to get out of my information bubble, and try to understand the other side, and also try to let's say find out what are the contradictory opinions, and then we can make a judgment. Because without that, it will be very difficult to build a sustainable future. Okay, so impact of HPC. Out of different UN sustainability goals, we did a huge progress. We moved, as I showed you, in different areas to really very good place. But nevertheless, there are still challenges that need improvement, and we can always improve our climate and weather models. We can always improve the way we simulate the let's say the medicines, the drugs, in terms of workloads, in terms of domains, especially in cloud HPC, what we see is a lot of proportion for biosciences, and bioscience was the early adopter for cloud HPC, therefore it's this proportion, but also weather modeling is catching up. This is the fastest growing domain right now on the cloud HPC, almost 30%. So let's have a look how Microsoft makes impact into those domains. First of all, we work directly with customer working on climate solutions, on weather solutions, weather simulation solutions. We have colleagues from head office that can tell you more about our collaboration. But we also work with renewable energy companies, like with Vestas. We also work with companies simulating oil splits or simulating chemtrails. So we work directly with those type of customers. Second type of customers is the customers who try to digitalize their very toxic, time-consuming processes. Example is Bridgestone, that they were able to replace completely physical testing of their tires with virtual prototyping. But it's not only direct collaboration with customers, it's also supporting different communities, different partners. And also we have come up with programs like AI for Earth, where everybody from the research can apply, and also planetary computer. So let me spend some time on the latter project. Planetary computing, despite its name, is actually a platform that brings together very large data sets, different kinds of APIs, and manage compute capabilities, so that the researchers can start very easily to model natural ecosystems. In terms of data sets, we provide different kinds of data sets, from remote sensing, weather, climate, land cover data, biodiversity. Right now we have about 12 petabytes of data. This amount is growing. And this is actually to meet the challenge of how do I share data between different HPC actors. Second, it's about APIs. So very easily you can create API queries for spatio-temporal to get some specific information about specific region in a specific time. And also you can run on top of it different kinds of calculations with open source APIs. And then it's also the way researchers can access it. So it's through Jupyter Notebook. And not only they can access to get data sets and APIs, but they can also get access to different compute resources for both embarrassingly parallel with Dask, but also with MPI-based calculations with Azure Batch, with InfiniBand and all what is necessary to write distributed computing. Another example, we've been approached by a startup here from Switzerland called Meteomatics, who worked very hard, many years, to optimize their WRF model. So right now, they have a model, high-fidelity kilometer scale model, with optimized parameterization, and they told us we need to run it within 1 hour, within one single hour. So after a few days of preparation, we were able to, within 30 minutes, we were able to create a cluster, InfiniBand interconnected, with latest AMD EPIC Rho Milan X. And we were able, with OS image that included all InfiniBand drivers, with all MPI, with MPI stack, and also with the software on top of it. We executed the simulation that lasts less than an hour, and then we shut the cluster down. And it took us, let's say, 2 hours to complete the whole test. So right now, we are able to perform this test on whenever it is needed. So today we are running this in production. There are 4 simulations per day, but we are moving to the place where we want to run it 24 times a day. And then if you see some details on the model coverage, you see some details in the terms of horizontal resolution, vertical levels. In terms of storage, we are generating around 1 petabyte data per month. And also, from a technical perspective, it is possible to downscale the model to actually 90 meters because of NESA terrain model of that resolution. So this is the a comparison of GFS 19 kilometer resolution with 1 kilometer resolution. As you see, we are able to capture some local effects, not only in terms of precipitation, but also in terms of cloud forming, in terms of hail, storms, and this is super important to deal with coming extreme weather conditions. So this is how this is an example of the result. But it's not only about weather modeling; it's about providing this as API. So that's really what makes we believe we are lowering the bar for different actors to consume the results of this simulation. So there is a concrete API definition from which you can call for the time sequence. You can request for specific parameter, specific location, and also in specific output. So right now there are about 1,800 different weather, ocean, and environmental parameters. There are forecasts up to 7 months, and also the climate scenarios up to a year to 2100, and also backwards for historical data computations. So that was the first example. The second example is about drug formulation. So today, the drugs are getting more and more complex. Specifically because of this complexity, it's untractable to simulate them with molecular dynamics, because you have hundreds of thousands of atoms usually. There is a special kind of drug which is called amorphous solid dispersion. Those drugs are provided in the amorphous form, which means their bioavailability is much better. They can be absorbed by the tissue much easier, but also they are less stable. They will basically recrystallize in different temperature ranges, and in order to provide it as a drug to different parts of the world, you have to add additional ligands, like for example polymers. So the challenge is that, first of all, you have to know the concentration of both API, active pharmaceutical ingredient, but also of concentration of polymers. And this is a super complex assignment, because you need to find out the right polymers with the right concentration, with the right API concentration, and this is an untractable problem. So, so it takes a lot of time to perform a physical testing in the laboratory to find the best concentration. Basically, you want to avoid recrystallization and so-called phase separation. You want to actually estimate some key metrics, which is like solubility limit specifically. So as an input, we are getting API and excipient definition, and then we are creating a supercell composed of the mentioned hundreds of thousands of atoms. Of course, it's not intractable to solve it with regular modeling, so we are actually we are transforming this supercell into, let's say, our model, and this which can be then solved in the classical way with DFT-based relaxation. And then we introduce the thermal motion, so which gives us, let's say, we are simulating how it behaves, and then we can do many different kinds of simulation. For example, we can simulate how the drug penetrates the cell membrane. So we are able with the, to actually simulate the cell membrane and then measure the penetration through partition coefficient. But not only that, we can measure different types of adhesions. If we're not talking about the drug, but we're talking about some other type of material. But in the end, we are getting the matrix of interest, specifically here, it's about solubility limit. So we validated this method with the experiment. This is the public domain ASDs. Experiment values were around 45. And let's say from the experiment, from the simulation, we were very close to that value. The same for another ASDs, 70-20, we were very close, 20-16. And which proved, this way we could prove to the pharmaceutical company that this is actually representing, we are able to represent the stress testing. So the outcome of this project is that we are delivering the drug formulation team a report with all those different metrics in terms of AS density, in terms of as a function of different API load. We are able to measure some concentration and the energy gap. We are able to also find out how the drug behaves with different temperatures. So the drug formulation team is actually interested in this recommendation, because then this way they can just go to the lab with a specific recommendation, and then they can save so many months of physical work, which is again taking time, money, and also it's toxic. Okay, which brings us to the last part of the presentation, challenges and opportunities. So first of all, I will talk a little bit about challenges in IT, and of course HPC is a part of this, so it's affected, and also about our future workforce. So how are we going to sustain the number of engineers, HPC engineers in future, and why we are struggling today? So first of all, many years ago, I still remember how globalization was the holy grail, how moving factories to another countries was a great idea to reduce the production costs, but also to reduce the carbon footprint. Very smart. And right now, because of zero COVID policy in China, some factory lines are completely suspended. They are not operational. People are not going to the factories again. And that caused the supply chain. Of course, there were other reasons, but that was one of the causes. So right now, the companies, including the automotive and chip producers, they are considering moving away to another countries. But it will take time, and before it happens. So there will be still challenges, in my opinion, on the supply chain. You have to wait many months if you order hardware today. The second, there is also a very interesting trend coming. It's called Teslafication. So Tesla was the first automotive company that actually signed a deal directly with the material producers, with raw material producers, with mining companies, so that they can reduce the supply chain complexity. And maybe it happens, or will happen in the chip with the chip companies. We'll see. The next challenge is raw material crisis. Not enough demand for lithium, for example. If you imagine 30% of the lithium demand is right now in the single place in Chile, it's just a salt lake. And so we have very few demand, and still we have this great ideas to move towards electromobility. Well, there could not be enough lithium. Then there is a noble gas shortage in the semiconductors industry. Who knows what happens next if we are seeing the similar constraints. And then the next challenge is energy prices skyrocketing. So right now, in some of the countries, energy prices went up by 100%. So it means that power and cooling costs will be more visible on the bill for the data centers, and will also penalize HPC projects. So there are some calculators, like I think EPFL was working on it, that you could actually get the CO2 and power consumption per job. So if you know in advance how many power you need, well, maybe you think if I want to run this job. So the projects will be penalized. Maybe the research will be penalized. And then there is an energy consumption challenge. So we are talking a lot about reducing that number, about reducing the energy use of data centers. But we are talking less about this number, which is the power consumption coming from internet traffic. So there are studies that say that actually Netflix alone and YouTube alone produce much more energy than data centers, all the data centers. Not mentioning how many energy is needed for beacon mining or pornography. The last point I want to make is about our future workforce. So we have to sustain the number of HPC engineers, software development engineers, and we see that we are struggling with this. And there are many reasons, and I don't want to debate right now, but for me what is striking is that silently we have shifted from reading to browsing. So as I remember as a student, I read a lot. I also had a lot of time to experiment with different types of codes, and I had time to do this. And today, let's say the millennials, the new generation, they don't have time. Why? Because they spend most of the time, their spare time on social media, and also a lot of hundreds of thousands of hours are spent on watching YouTube movies, playing games, or watching how the other people are playing games. So there is this time that we used for actually develop ourselves is right now gone for the new generation. And it's not only that. There are some social effects of when using devices, using screens, and there are studies showing diminishing problem-solving skills, diminishing memorization skills. There is a new phenomenon at schools. It's called continuous partial attention, which means that students are no longer able to focus on a single topic. They have always to do some other stuff in terms of hanging out for the phone. And also continuous distraction. So we are constantly distracted by the devices. It's very difficult to focus, and even from the CEOs of major companies, they put this problem as the first challenge that they see in their businesses. Social media, it's impacting our life. There are more than 80% of